Okay. All right, so your test is going to be on Friday. Let me start off by doing this. Let me start off by going to the very back of your packet, page 45, and show you what to expect on the test. Okay, there's going to be an extended implicit differentiation problem. Find the derivative, finding may involve product rule, maybe, and then asking you to find tangent line equation, vertical and tangent, vertical and horizontal tangents. And I'll show you an example of that, what it will look like. A graph problem, where I give you a product rule, either product rule, quotient rule, chain rule. You have to recognize the relationship between the functions, apply the appropriate derivative, and then use the graph to either pull order pair or slope. A derivative problem involving power rule, product rule, quotient, chain, implicit could be, yeah, so I'll show you one of those where a combination problem here. And then a particle motion problem, similar to the one that we did on the quiz. But I think the only thing that is added to it is something like displacement and the total distance. Okay, so displacement is just change in position, final position minus initial position. And the total distance, we got to find the original positions, beginning and end, look to see if there's a place where there's a change in direction, identify that position as well, and then just count your steps between each of those places, right? Every step is positive. We'll do an example of that. And then the differentiable piecewise problem, which we did in class, and we can do another one today. All right. So, it'll be 3 pages. You'll get to use your calculator, so make sure you bring your calculator on Friday. And what the test will look like will be a lot like what you see here on this morning review, this review session problem, page 39. Okay, I'm going to save to go over this on Friday, but if you guys have time, I think it'll be good for you to work through it, because if you can work through these 3 pages, you should feel pretty comfortable for the test. There's no surprises on the test. So if you can do these topics well, you should be ready for the test. So let me show you what that looks like. So you have a piece, you have a this is on page 39. You have a implicit problem with a little bit of what here? What do you notice there? What other? Oh, the dydx. Okay, yeah. So dydx with implicit, but what does the xy tell you? Product rule. And we've got to watch out for the what? The minus. The negative, yeah, distributes through, right? Okay, so find the derivative, find points on the curve, just insert the 0 into the function, right? Okay. Yeah, tangent line equation. So find the order pair and slope, write the equations of the tangent lines, and then set up to find vertical and horizontal tangent. We talked about yesterday, horizontal tangent, you set the numerator of the derivative equal to 0, and then for vertical tangent, you set the denominator of the derivative equal to 0. Okay. We have differential. We have solving for A and B. If G is differentiable everywhere. So if you see the word differentiable, just understand it means two things. It means continuous and differentiable, but rather than saying continuous, they just say differentiable. So just, but we have to go through two columns, right? Treat A and B like constants. Okay, so we'll go through an example of that, but I'm going to save this for either for you to do on your own or wait for me to do it on Friday with you. And then this is problem where you're given finding the derivative. And then you got to decide, is it product rule? Is it chain rule? Is it chain rule? Is it quotient rule? Find the derivative. And then once you have the derivative, you plug in the numeric value, and then you pull that information from the slope. You're either from the graph, you're either pulling the order pair or the slope. Okay. A problem like this, where you have to go through chain rule and quotient rule. And then finally, particle motion problem. Notice that all these things you've been asked about for the most part: finding average velocity, finding average acceleration, displacement, total distance, increasing speed, decreasing velocity. So make sure you clear up if you have any misunderstandings from the particle motion portion on the quiz. Make sure you get that cleaned up, because you're gonna see those again on the test. Yeah.
So proportional with the graph, like you said, like look on different points of the graph.
Or
do you do anything?
Oh, you mean problem like this one
Yeah.
here? Yeah. We can maybe go over a example of that in class. We did that yesterday, but we can go over it today again if you have time. But I can go over it with you too later. Okay, and then so that's what the test looks like: 3 pages, and then the key is attached 42, 43, and 44. So if you spend the time to go through this beforehand or work through it multiple times, you should feel ready for Friday's test. Okay, but I'm not going to go over this in detail until Friday. I want you guys to do that. I do have a video recorded from previous year when I went through of going over these 3 pages. So I'll make sure that is available on this year's pages, so that if you want to click and watch that video after you go through it, you can have that option. All right. So this is test review, page 29 here. Okay, it says find the average rate of change. Average rate of change on the interval from 1 to 3. So we do if we did instantaneous rate of change, but it's the average rate of change. So average rate of change is just what? Okay, or what's another way of saying it? Can you say it a different way? It's the slope. Okay, it's the slope of this function. Okay, slope between these 2 points. So that's what average rate of change is. So average rate of change, there's no calculus involved. Instantaneous rate of change, then it's asking for, right, the specific derivative. So this is kind of like average velocity, right? Average velocity, you just do the slope of the position function. So average rate of change is just f of 3 minus f of 1 over 3 minus 1. Rate of change is slope. Average rate of change is slope between 2 points. Okay, so let's find f of 3. What's f of 3 equal to? Okay. What's f of 1 equal to? Okay, slope between the endpoints here. So 0 minus 0 over 3 minus 1. That's just 0 over 2, which is 0. Instantaneous rate of change at the endpoints. So you're going to get two different slope values. Now I can find the derivative and plug in 1 and 3 into each of those derivatives, or into the derivative function. Okay, so what's f prime here?
Four minus 2x.
So the instantaneous rate of change, just plug in the 1 and 3 separately, and there's going to be two different slopes at 1 and 3. All right, what does this notation mean here? d2y over dx2. Second derivative, okay. But we're not going to do that. That's a little bit too much for what I expect from you right now. So let's just find the first derivative, okay? But if I want to find the first derivative, how would you go about setting this up? Or how would you do first? Yeah, let's get that radical to go away to make it a little bit easier to read. We just want to find the first derivative. What's involved here to find the derivative? Chain. Outside, inside, right? All right, so go ahead and try that. Okay, outside's derivative. What goes in here? Times 2. Good. And I just want you to clean up in a sense of putting it under one fraction with no negative exponents. So if I try to clean all this up here, what will remain in the numerator? Okay, what happens with that 2? Yeah, that 1/2 and 2 will do what? Cancel each other out. So the only thing left is just the x. And what can I put in the denominator? Yeah. So we're not going to get to the second derivative. We'll just.
Can you make it like x plus 1 to the square root of 1/2? Like simplify it.
You mean distribute the 1/2 through?
Yeah.
No, we can't do that. Yeah. Now we can do that if it was, let's say if it was x squared times 2, or let me say this, 2x squared to the 1/2. I can distribute this through, but I can't distribute this through. Why is that?
Oh, use the plus sign.
That plus sign, yeah. Anytime there's a plus or minus, just know that it's going to complicate the things that you wish you can do. Yeah. Oh, this right here? That just means find the second derivative, which we're not going to do. Yeah, it's just a little bit more involved than what I need us to do. Yeah, this is a very specific notation. We're not squaring anything. This is just the notation that is developed for the second derivative. We just have to be able to recognize it. That is just a symbol. That just means find the second derivative.
And you keep it in dy dx like after. You don't change it back to y.
Oh, you can, there's different variations. You can say it's y prime or f prime of x or dy dx. They all mean the same thing. They all mean first derivative. Okay, number 4 here. If the line tangent to the graph of the function at point 1,7 passes through the point -2, -2, then f prime of 1 is equal to. So let me draw a picture of this to maybe help you see what's happening here. So we have a tangent line to the graph, and that tangent line is going to go through these 2 points. So 1,7 and -2, -2. So here's my tangent line. I know that this tangent line is going to be, okay, first of all, we know this, sorry, this line is going to be tangent to the graph at the point 1,7. So whatever, we don't know what the graph looks like, but maybe something like, I know it's a curve, maybe something like this. Now, do I know the slope of this line here? Can I find out the slope of this line? Okay. And what does this tell us? If the line is tangent to the graph, what does that tell us about the curve at that point? Okay, it touches it, but something else shares the same slope. So that's the key here. So that means if I can find the slope of this tangent line, of this, sorry, of this this line here, then I know that must also be the same slope as the curve at that point. All right, that's what that word tangent tells us. So let's find the slope of that line, and the slope of that line would indicate the slope of the curve at that point as well, because that's what this means. So here's my slope. So changing y, we're changing x. So the slope of the line is 3, and the slope of the curve at that point must also be 3. Because if I have a line that is tangent to a curve at a point, that means they share the same point and they also share the same slope.
How are you able to draw that red line? Like, where did you get that from?
I didn't know what the graph looks like. I just knew that at that point it's gonna be the exact same slope as the curve. I just gave it a random example, but the key thing is that that slope there is going to match the slope of this line. Yeah.
So like anytime it says the slope of a tangent, it's just all you do is just find the slope and that's it. So
Yeah. So basically, anytime you have a statement about a line that is tangent to a curve, just understand there's 2 things going on here, that they share the same points and that the graph and the line will also share the same slope. So sometimes it's easy as doing that, but other times it's other applications. But that's the big takeaway for us, to just understand that there's that relationship there. Okay, we did a problem like this yesterday, and we can talk about this as well. It says find a and b such that the piecewise function is differentiable everywhere. So this really means 2 things here. They're leaving out the word continuous, but continuous falls under the umbrella of differentiable. So I'm just going to write this way here. It's continuous and differentiable. So what that tells us is that the continuous portion tells us that we want these 2 graphs to line up nicely where they share the same y value at x equals 3. But the differentiable portion says that we want these to not only line up with the same y value at 3, we also want the 2 different graphs to do what at 3?
Intersection.
Okay, which means the same point, but same y value. But we also want them to share the same what?
Rate of change.
Slope. Yeah, same slope. So that means the continuous portion means that we can set the equations equal to each other because the y values are going to be the same. We can also set the derivatives equal to each other because we want the slope to be the same. So, so we know that they share the same y value, but just not anywhere, not just anywhere, right? Only at x equals 3. We only care about them share the same y value at x equals 3. And we also know that we want them to share the same slope at x equals 3. Okay, let's do the portion without the calculus, where we're just setting the equations equal to each other. So ax cubed equals x squared plus b. We want these two graphs to meet up at the same y value. But again, we don't want them to share the same y value anywhere. We only want them to share the same y value at x equals 3. So I can replace every x with what? With 3. All right. So this is as far as I can go because I have two missing values, two unknowns, and I can't solve for either A or B, at least not with the help of another equation. So I'm going to pause here and see if I can make some progress with the other one. So if I wanted to share the same slope, I first have to find the what? Derivative. And something we ought to keep in mind is that A and B are not variables. A and B are constants. So you treat A and B like how you would constants.
Why is A constant?
Yeah, sorry, it did not specify here. But on the test, I will say A and B are constants. So these values are set in stone. We just don't know what those values are. Now, X can change, but A and B cannot. It's just an unknown constant. So you're going to treat A and B the same way that you would as other constants, like a 3 or a 5 or a 6. So let's just go ahead and build the derivative first, and then we can set them equal to each other. So imagine this was 5x cubed. Okay, let's just pretend that's the case. What's the derivative of 5x cubed? 15x squared. Okay, so therefore, what's the derivative of ax cubed? 3ax squared, right? The a is not going to go anywhere. It's just going to tag along in front of the variable. Okay, remember b is a constant here. What's the derivative of x squared plus b? Just 2x. And the b goes to a 0. Right? Goes to a 0. Right. So we have our two slope formulas. We're going to set them equal to each other. We're going to force them to share the same slope at x equals 3. Replace every x with 3 because we only care about them sharing the same slope at that point. So we have some resolution here, right? I can solve for a. Can reduce it. Oh, no, I can't. Yeah, I can. 3, I can get 2/9. And I can solve for b, right? Well, I know 27a is 6, so that's a easy substitution that I can make here. So b is equal to -3. Okay, so you see a problem like this on the test. Any questions here?
So how do you get the 2/9? Oh, do you just like simplify it, or you get the 2/9?
Oh, the 6/27?
Yeah.
Yeah, I just reduced it. I divided 6 by 3 and 27 by 3, and I got 2/9.
What is slope intercept?
We're just solving for a and b. We're not writing the equations. Yeah, so whatever a and b's are, then that's our answer. Yeah. So these A's and B values will cause this function to line up nicely where they're going to meet up at 3, and they're going to have a smooth transition with the same slope at 3. So we're not seeing the graph, but we don't need to see the graph for us to. We just have to be able to know how to go through this process.
Is that like all needed yesterday?
Yeah, we did that yesterday. Yeah.
What's the difference between like just being continuous, well, forever, and it being continuous and differential?
So the word differentiable means a smooth curve. So we can't. If I say the word differentiable, it already means it has to be continuous to begin with. So a lot of times, if it's like an AP exam problem, they're not going to say continuous and differentiable. They're just going to say differentiable. But I like to say continuous and differentiable for us to recognize that there's two things that we're after. We're after the same, sharing the same y value, which is the continuity portion. We're also after the same slope, which is the differentiable portion. So I'm just breaking that word into two components and having us treat it like two separate processes. But sometimes on the test, they may not say continuous, they may just say differentiable. We just have to know that, okay, there's two categories we just have to remember about the continuity portion. Okay, why don't we do a full or a relatively full particle motion problem? So page 30. Okay, a particle moves along a straight line according to the given equation. So here's your position function. Oh, sorry, next. Position function, and t is greater than or equal to 0. Find when the particle is moving left, find when the particle is velocity is increasing. So there's a lot of things we got to do before we get to part A. So before I can find particle moving left or right, I first have to find what? Velocity, yep. And then set the velocity equal to 0, create your velocity sign line, and then test your signs, right? So basically, before maybe a problem would split that into 2-3 steps, but here we're going to do it all in one step. Okay. So I'm going to do the work up here so I can just have enough room to do everything. So I'm going to find the velocity, set velocity equal to 0, create my velocity sign line, populate my velocity sign line, and then test the positive and negatives.
Can you find acceleration too, like so?
Actually, let's see this problem. Yeah, normally I
Like for like future problems, like
yeah, future problems. Yeah, I would say yeah, I can find acceleration as well. But I think usually if that's the case, I will prompt you for it. But if you need it, then yeah, let's go ahead and do that. It doesn't hurt. Let's just go ahead and find velocity and acceleration. All right, I want to make sure I don't run out of room, so I'm going to use that upper portion there. Okay, what's the derivative here? What's velocity going to be? Yeah. Acceleration is easy. We'll just get that out of the way as well. Okay. All right, so next step, let's find set velocity equal to 0. Factor your GCF out. My critical points are 0 and 2. Yeah, 2t will produce 0. T minus 2 will produce 2. There's 2 t variables, so I'm looking for 2 t values there. Okay, my velocity sign line. Now 0 does end up being a place where there's no movement, so we know that 0 is going to be a place where the particle is at rest. Okay. We're going to do test points. But remember, these test points have no other purpose except to fill up the signs. The 1 and 3 that I'm choosing have no other place in the problem. Okay? We're just using the 1 and 3 to figure out what the signs are, and then after that, we don't care about those numbers anymore. Okay, so I plug 1 into the velocity function. 1 times 2 is positive, right? 1 minus 2 is negative. Positive and negatives gives me negative.
Positive.
Plug 3 in, yep, both positive. Okay, and I can cross these numbers out, right? The 1 and 3 is not gonna mean anything for us anymore. Find the particle when find when the particle is moving left. Moving left in which interval? 0 to 2. Now, if I test 0, because 0 is a part of my domain, if I plug in 0, I still get slopes velocity 0. So I'm not going to include 0 in the movement of left, because at 0 the particle is at rest. And what's the reasoning here? Because velocity is negative, or I'm going to say less than 0. Okay. Find when the velocity is increasing. What does that mean?
Oh, like to the right, like.
Yeah, but and this is this talking about velocity?
Acceleration.
About acceleration. So in other words, find when acceleration is what? Positive. So let's create our acceleration sign line, and we can decide when acceleration is positive, right? So we'll set acceleration equal to 0, create our acceleration sign line, and look to see which interval do we see acceleration positive. Again, we're including 0 because that is a starting point. We'll test our acceleration sign line here. So if I plug 1/2 in for t, 1/2 minus 1 is negative. If I plug in 2 in for t. So velocity is increasing in which interval? 1 to infinity. Yeah. Because acceleration is positive. Okay. Find when the speed is decreasing. Now, if I want to find increasing, decreasing speed, what needs to happen? We got to do somewhat. This is not the same thing as velocity increasing, decreasing. We got to look at velocity acceleration. So I think the easiest thing to do is let's just line up. We have both sign lines. Let's line everything up and see where are the signs going to be what? What are we looking for? Signs to be opposite. So I'm just going to copy down my sign lines I've already created. Line everything up. See how they compare. Okay, I try to line everything up as clear as I can make it. Where do you see, which intervals do you see velocity and acceleration not having the same signs?
Which we wanted to.
1, 2, right? Let's just compare and convince ourselves, right? Because from 0 to 1, they're both negative, so we know that speed is increasing. But between 1 and 2, one is negative, the other is positive. So this interval, we know speed is decreasing. But then from 2 on, they're both back to positive, so speed is increasing.
So when they have opposite signs, that's where you know speed.
That's right, when speed is decreasing, that's right. But if both are the same signs, then speed is increasing.
Even if they're both like negative, still.
That's right, because they have the same signs. Okay, where's the particle located when the velocity is 0? Let's do this first. When is the velocity 0? Zero and 2. So it's just asking, find the position at these moments. So how can I find the position at these moments? Plug into the position function. Yeah. So if I plug 0 in for t, I get -1. If I plug in 2, it's a little messier with fractions, but you'll get to use your calculator. Ends up giving us -11/3. So that tells us that's a location on the number line. It's like somewhere like around like -3 point something, or close between -3 and -4. Okay, everybody good so far?
So you see the position?
Yeah, because it says where is the particle located. So where is the location question? Location deals with position.
And just to answer, you just keep like that.
Yeah. These are just locations that sit on the number line. Okay, part E, find the particle's displacement. What's the formula for displacement? Yep, final position minus initial position. Yep. So we don't touch velocity, we just use position. S(3) minus S(0). If we get a positive number, great. If we get a negative number, great. We just take whatever number they give us. Okay, so actually, they end up being in the same spot, so my displacement is 0. Okay, particles' total distance is a bit more than displacement, even though we are still going to use information from displacement. So with total distance, we have to involve S(0) and S(3), which we can do. But then we have to ask ourselves, is there a point where this particle is going to change direction between these moments? Because if there is, we got to keep track of that location too. At 2, right? At 2, the particle does change direction. Now, if there was no change in direction, then you would just do S(3) minus S(0) and the same process. I think the only thing that's different from displacement, if there's no change in direction, is that if you see a negative value, you got to make it a what? You got to make it positive, right? That's the only difference between distance and displacement, potentially, if there's no change in direction. Right. But here we have change in direction, so we have to locate both these places. I think we gathered some of this information already, right? So S(0) is -1, S(2) is -11/3, S(3) is back to -1. So when you find distance, don't think of this as, oh, I'm going to add these together, okay? What you want to do is you want to think about it as, okay, I'm walking between these locations, and how far have I traveled between these locations? So it's a little messier here with fractions, but let's say here's -1 and here's -11/3. I know the steps analogy doesn't quite work with fractions here, but you're walking from here to here, and then you're walking back. So how can I find the distance between 2 points? Just do what?
Add them together.
Yeah, I'm not going to add together. Or let me make it easier here. Let's say you want to go from 2 to 7.
Oh, you
Subtract it, right? So what's -11/3 minus a -1? That's -11/3 plus 3/3, which is 8/3. Now think of it as it's a distance, so you're going to make every quote unquote step you take positive. So it takes 1/3 step to get from here to here, and then if I walk back, it's also 1/3. So in a sense, I've taken those many steps. I'm going to add those together. So my total distance is 16/3. Maybe, but if it is, I mean, you have your calculator.
I just realized something. So for D, how do you know that, like, I just realized, how do you know velocity is 0 at 0 and 2?
I think we found that at the beginning, right? Beginning, we set velocity equal to 0, and we populated our velocity sign line. Right? We set velocity equal to 0. We solved for t. We got 0.
So you recommend doing that at the beginning too?
I think we did it because we had to get to part A, so it's just a natural progression to get the information that we needed for part A. Okay, part G, is the velocity increasing or decreasing at t equals 2? Okay. What is this asking? Careful. Is it asking about velocity? Yep, so it's acceleration. So it's basically saying what's happening with acceleration at 2. So let's plug 2 into in for acceleration. 4t minus 4, that's my acceleration function. My acceleration is equal to what? 4, what does that tell me? Velocity is increasing because acceleration is positive, yeah. I'm sorry, my bad. Not vehicle. Yeah, acceleration, thanks. Find the velocity and position when acceleration is 0, okay? Do we know when acceleration is 0?
0 was 14 minus.
Do we know the time when acceleration is 0?
No.
I think we found it earlier. Did we find it earlier?
0 and 2.
Well, that's when velocity was 0. When is acceleration 0? 1, right? We set acceleration equals 0 up here. We solve for t, we got t equals 1. So we can just find the velocity and position at 1. Okay, plug 1 into the position function. You get negative 7/3. Velocity at 1, plug 1 into the velocity. I get negative 2. Yeah, so plug, let's see, 1 into the velocity here. 2 minus 4 is negative 2. Cross off 7 and 8, you won't see these limit definition problems.
Is that from last unit?
Hmm?
Is that from last unit?
It's from 2.1 where we did the limit definition of derivative at the very beginning, but yeah, it's more minor. We'll leave that off. Okay, let's talk through number 9 here. Find the points where the graph has a vertical or horizontal tangent. So what's the procedure here? First, we have to find the what? Derivative. Okay, look at how this is set up. What would you use to find the derivative?
UIDX.
Implicit, right? UIDX with implicit. How many y's do you expect from your derivative? 2. You see 2 different y's at the beginning. Okay. Now, once you find the derivative, you have a numerator and denominator. And then how would you find your horizontal tangent? Set the numerator of the derivative equal to 0. And then to find vertical tangent, set the denominator of the derivative equal to 0. Okay, so let's just see if we can spend the next 35 minutes working through it. And then if we don't finish, we can finish tomorrow, but try number 9. Okay, do we need any product rule here, or is power rule good enough for all these terms? Power rule, yeah. We don't see any x and y's attached together, right? Okay, keys on the next page. You can check your progress if you're ahead of me. Now, when you set your numerator or denominator equal to 0, it's only going to give you a partial location of your order pair. So if I only have a partial location, how can I find the full order pair? Back into the original, yeah. So if I don't have the full information, it's okay. The original equation will get you that full order pair. I took the GCF out of my derivative, but you don't have to. It would be the same. It just makes it a little bit cleaner, potentially with smaller numbers, but don't worry about, oh, I gotta take a GCF out. Just, you can leave your answer, your derivative as 8 minus 8x over 2y plus 4, and you'll get everything you need as well. Yeah.
Go for the 8 ones.
Uh-huh. I changed the signs here, so plus 8 minus 8x. Then the terms that have dy dx, I can factor it out and divide over. Horizontal tangent, you set the numerator equal to 0. You'll get x equals 1, but 1 is not the full order pair. Plug 1 back into the original equation. And in this case, there were 2 order pairs, 2 locations where there is a horizontal tangent line.
Is there more for you?
Yeah, and the vertical tangent. Set the denominator equal to 0, solve for y. In this case, solve for y because that's the variable there, and then plug it back in to the original to get your order pair. Okay, tomorrow we're going to do portions from worksheets, test review worksheets 2 and 3. But if you want to go again, head start in terms of preparing for the test, you can work through worksheets 2, 3, and 4 if you like. I have an afternoon help session. I'll pick out problems from worksheets 2 and 3. And then Friday morning, I'll do worksheet 4. But tomorrow we'll just pick out problems from worksheets 2 and 4. Okay, so start studying for your test. That's your no homework, no official homework, but start studying for your test for Friday. All right, come get your phones.
Do you do anything else new besides the piecewise?
We did piecewise, we did this horizontal vertical tangent, and we did the graph where you have to find the chain rule and or product rule and B.
How does the graph one work? Can't be seen like that.
Okay, appreciate it.
Thank you.
So on page 21 here, you see how this is f of x, g of x. We go through product rule. I think we may have done this in class the day before. And then once you find the derivative, plug in 1 into the derivative. And then you're just pulling information from the graph. Either you're pulling the order pair or the slope, depending if it's f of 1, g of 1, or if it's f prime of 1, g of 1.
Okay. Oh yeah, I remember you saying that these turns are like undefined, right?
That's right. Any sharp turns has a slope undefined. Any flat surface is a slope 0.
Okay. And what's that one for the last year?
That'll be a slope 0.
Okay.
It's a nice curve.
That's right. All right. Thank you.
20.
Fast forward.
Probably the fastest course.
Okay.